We rely on electricity for almost everything. When something goes wrong, it can be frustrating and even dangerous. That's where electrical fault finding comes in. It's like detective work for electricians. We need to track down the source of the problem and fix it. This keeps things running smoothly and prevents accidents. Think about it, a faulty light switch is annoying. But a major electrical fault can shut down a whole factory. This can cost a lot of money and even put people's safety at risk. Knowing how to find and fix electrical problems is a critical skill. It's also important for anyone who works with electricity to understand the basics. Electrical systems can be complex, but the basic principles are the same. By learning how to identify and troubleshoot common problems, we can keep the power flowing and stay safe. So, let's dive in and learn about single-phase and three-phase systems. Let's start with single-phase power. It's like a one-lane road for electricity. It's commonly used in homes and small businesses. Single-phase systems use two wires, a hot wire and a neutral wire. The hot wire carries the electrical current, and the neutral wire provides a return path. Now imagine a three-lane highway. That's what three-phase power is like. It's more powerful than single-phase and used in factories, large buildings, and heavy machinery. Three-phase systems use three hot wires and one neutral wire. These wires carry alternating current, but they're slightly out of sync with each other. This creates a smoother and more efficient flow of power. Think of it like this. Single-phase is like pedaling a bicycle with one leg. You can still get where you need to go, but it takes more effort. Three-phase is like pedaling with both legs. It's smoother, more powerful, and you can go further. Understanding the difference between single-phase and three-phase power is crucial for electricians. It helps us choose the right tools and techniques for the job. Now, let's move on to voltage levels. These can vary depending on the system. Voltage is like the pressure of electricity. It's the force that pushes the electrical current through the wires. Different electrical systems use different voltage levels. Homes use 120 volts for most appliances and 240 volts for larger ones. Industrial settings use higher voltages like 415 or 1000 volts. Higher voltages allow more power with less energy loss, but they pose a greater risk of electrical shock. Understanding voltage levels is crucial for safety. Have you ever heard that faint humming sound near electrical equipment? That's the frequency of the alternating current at work. In most parts of the world, including the United States, the standard frequency is 60 Hz, meaning the current alternates direction 60 times per second. Other countries, like those in Europe, use a frequency of 50 Hz. This frequency is important for several reasons. It affects the operation of electrical motors and other equipment. It also plays a role in how electricity is generated and distributed through the power grid. The frequency needs to be kept within a very narrow range for everything to function properly. Imagine a group of people dancing to music. The beat of the music is like the frequency of the electrical current. If everyone dances to the same beat, everything flows smoothly. But if some people are off beat, it disrupts the rhythm. Similarly, maintaining a consistent frequency is essential for the stability and reliability of the electrical grid. Now, let's move on to troubleshooting energy meters, which are essential for measuring electricity consumption. Energy meter troubleshooting step-by-step guide. Energy meters track your electricity usage. Sometimes they malfunction. Here's a step-by-step guide to troubleshoot common issues. Step 1, check the basics. Ensure proper connections. Step 2, inspect the display. Consult the manual for error codes. Step 3, check for overheating. Contact your provider for repairs. Section 6. Electrical motors powering our world. Electrical motors are everywhere. They're the workhorses that power our appliances, tools, and machinery. From the tiny motor in your electric toothbrush to the massive motors used in industrial pumps, these devices convert electrical energy into mechanical motion. There are two main types of electrical motors, AC motors and DC motors. AC motors run on alternating current and are commonly used in household appliances and industrial machinery. DC motors, on the other hand, run on direct current and are often found in battery-powered devices and electric vehicles. Within these two main categories, there are various subtypes of electrical motors, each with its unique characteristics and applications. For example, induction motors are a common type of AC motor known for their reliability and low maintenance requirements. Brushless DC motors, on the other hand, offer high efficiency and precise control. making them suitable for applications like robotics and computer hard drives. Section 7. Mechanical motors and their applications. While electrical motors are prevalent, mechanical motors also play a vital role in various industries. These motors rely on mechanical energy, such as compressed air or hydraulic pressure, to generate motion. One common type of mechanical motor is the pneumatic motor. These motors use compressed air to drive a piston or rotary vane, producing rotational or linear motion. Pneumatic motors are often found in applications where sparks from electrical motors could be hazardous, such as in mining or chemical processing plants. Another type is the hydraulic motor. These motors use pressurized fluid, typically oil, to generate mechanical power. Hydraulic motors are known for their high power density and ability to operate at low speeds while delivering high torque. They are commonly used in heavy machinery such as excavators, cranes, and agricultural equipment. Understanding the different types of mechanical motors and their applications is essential for anyone working with industrial machinery or equipment. By selecting the right motor for the job, we can ensure optimal performance, efficiency, and safety. Section 8. Safety first. The final word on electrical fault finding. Working with electricity can be dangerous if not done safely. Always remember to disconnect the power source before working on any electrical equipment. Never work on electrical systems when wet or standing in water. Use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. If you're unsure about any aspect of electrical fault finding or repair, it's always best to consult a qualified electrician. They have the knowledge, experience, and tools to diagnose and fix electrical problems safely and effectively. Electrical fault finding is an essential skill for electricians and anyone who works with electricity. By understanding the basics of electrical systems, voltage levels, frequency, and troubleshooting techniques, we can keep the power flowing safely and efficiently. Remember, safety should always be the top priority when working with electricity.